Good morning. Today we are going to continue with the integrals of special functions. In the previous video, we have seen three results. One is the integral of dx over x squared minus a square. Another one was dx over a squared minus x squared, and the last one was dx over x squared plus a squared. And we found that the three results are: this is equal to 1 upon 2a log of x minus a over x plus a plus a constant. This one came out to be 1 upon 2a log of a plus x over a minus x plus constant, and the last one came out to be 1 upon a tan inverse x upon a plus a constant. So today we are going to go to the next set of three integrals of special functions which are somehow related to these. That is, we are going to take up the integrals of square root of these functions, that is 1 upon square root of x squared minus a squared into dx. Then we'll take up 1 upon square root of a squared minus x squared into dx, and the last one would be 1 upon under root of x squared plus a squared into dx. So this becomes the first one, this is the second, this is the third. Now coming to the fourth one, that is 1 upon x squared minus a squared whole under root into dx. Now though here there is a difference of two square terms, so we can factorize it, but it doesn't help us because of the presence of the square root sign. Okay, so factorization, as we did in the case of the first and the second result, is of no use to us for this function. So instead what we do is we proceed in the same manner as we proceeded in the third result, that is, we'll make use of substitution. And we know that sec square theta minus 1 is equal to tan square theta. So using this result, we will assume now here instead of x squared minus 1, we have x squared minus a squared. So if I put x is equal to a sec theta, this one becomes what? A sec squared theta minus a squared, which becomes a squared tan squared theta. Okay, so now dx is equal to a sec theta tan theta into d theta. Substituting, we get I is equal to, in place of dx we'll be writing a sec theta tan theta d theta whole upon, and then we write in place of x we'll be writing a squared sec squared theta minus a squared is as it is. We take out a squared common, we are left with sec squared theta minus 1, which is tan squared theta, and so it gives you a sec theta tan theta d theta whole upon under root of, if we have taken a squared common, we are left with tan squared theta. Now what we get is, again write it as a sec theta tan theta d theta, and in the denominator the square root and the square, they get balanced, and we are left with a tan theta. Tan theta gets cancelled, a gets cancelled, we are left with sec theta d theta. Now what have we substituted? We have now here before substituting back, what we do is, so this gives us I is equal to, now integral of sec theta is log of sec theta plus tan theta plus a constant. Now at this stage we have to substitute back theta in terms of x. So now we observe, but x equal to a sec theta, which gives us sec theta equal to x upon a. Now also we know that we have that there is a relation between sec and tan, and so we have from here we can have sec square theta is 1 plus tan square theta, or tan square theta is sec square theta minus 1. So we can have tan square theta is sec square theta minus 1, and this gives us tan square theta equal to x squared over a squared minus 1, which can be written as x squared minus a squared upon a squared. Now let's start substituting back. So what we get is I is equal to, now here what we have is integral is already solved, so we have log of. Now in place of sec theta we'll write x upon a, plus in place of tan theta we'll write square root. So we write square root of x squared plus a squared over a squared plus a constant. Okay, now here this a can be taken common, because from the square root you can take out a common. This can be written as log of x plus under root of x squared plus a squared. Now here let's write it as c1. Any some constant, here I am writing it as c1. Now what I get is upon a, so becomes minus of log a plus c1. Now log a is a, but log a equal to a constant, and so this term minus log a plus c1 can be replaced with some other constant, that is capital C, and so we get the next integral as integral of dx over square root of x squared minus a squared is equal to log of modulus of x plus under root of x squared plus a squared plus a constant. This is the result. Now exactly on the same lines we do the next result, that is the next result is integral of dx over square root of a squared minus x squared. Now again exactly by having the same argument as the previous one, we see that though a squared minus x squared can be factorized, but because of the presence of square root it doesn't help us, and so instead of factorizing it we will substitute. Again we know that 1 minus sine squared theta equal to cos squared theta. Here it is a squared minus x squared, and so we put x equal to a sine theta, we get dx is equal to a cos theta d theta. So substituting we get, therefore I is equal to, in place of dx we'll write a cos theta d theta whole upon, now square root of a squared minus, in place of x we'll write a sine theta, so a squared sine squared theta. Now this gives us a cos theta d theta whole upon square root of, now if you take a squared common you will be left with 1 minus sine squared theta, which is cos squared theta, so a squared cos squared theta, and I comes out to be integral of a cos theta d theta whole upon a cos theta. Now this cos theta gets cancelled, a gets cancelled, we are left with only d theta, which gives us theta plus a constant, and so I comes out to be, now again x is equal to a sine theta, so from here you get sine theta is x upon a, and so theta is equal to sine inverse x upon a plus c, and so we get the result of dx, that is under root of a squared minus x squared, comes out to be sine inverse x upon a plus a constant. Now let us come to the last result, that is integral of dx over x squared plus a squared. Now here in any case there is a presence of plus sign between two square terms, and so we can't factorize it. So the only way of doing it is by substitution. Now again we know that 1 plus tan square theta equal to sec square theta, and so we put, now again because same way as before, because of the presence of a square term, we have x is equal to a tan theta, and so this comes out to be dx becomes a sec square theta d theta, and substituting we get, in place of dx we'll be writing a sec square theta d theta whole upon square root of, instead of x we'll write a tan theta, so a square tan square theta plus a squared. Then proceeding exactly as above, we get sec square theta d theta whole upon a squared is taken common, sec tan square theta plus 1 is sec square theta whole under root, and this comes out to be integral of a sec square theta d theta whole upon, after taking the square root it becomes a sec theta. Now a gets cancelled, one sec gets cancelled, we are left with sec theta d theta, whose integral is log of sec theta plus tan theta plus a constant, let's write it as C1. Now proceeding exactly as the fourth result, we start substituting back. So what do we get? I is equal to log of, now here tan theta is x upon a. Okay, so in place of tan theta we write x upon a plus, now here sec theta is to be substituted back. Sec is equal to sec square theta equal to 1 plus tan square theta, and so you will have square root of 1 plus tan square theta, that is 1 plus x squared over a squared plus a constant. And when we simplify it further, we get log of, let's write this term first, that is x plus a squared plus x squared whole under root, and we take a common denominator which is a. Here it is a squared but square root, which comes out to be a plus c1. Again writing it as log of x plus under root of a squared plus x squared plus c1 minus log of a. Log of a is a constant which gets absorbed with c1 to give us another result, and hence the result for this integral comes out to be integral of x squared plus a square under root is equal to log of x plus under root of a squared plus x squared, or x squared plus a squared, whatever way we want to write it, plus a constant. And this is the sixth result which we have got. In this way we have done all the 6 results, that is we have done the 3 results in the previous video, that is the integral of 1 upon x squared minus a squared is 1 upon 2a log of x minus a over x plus a. That of 1 upon a squared minus x squared is 1 upon 2a log of a plus x over a minus x. The third one was 1 upon x squared plus a squared is equal to 1 upon a tan inverse x upon a. And today we have done 3 more results, that is integral of 1 upon under root of x squared minus a squared comes as log of modulus of x plus under root of x squared plus a squared plus a constant. The fifth result, which is the second result for the day, is integral of 1 upon under root of a squared minus x squared is sine inverse x upon a plus a constant. And the last one is that the integral of 1 upon under root of x squared plus a squared is equal to log of x plus a squared plus x squared plus a under root plus a constant. Okay, so with this we have done the first 6 special integrals, and in the next video we'll be taking up exercise 7.4. We'll be taking the next exercise, which is exercise 7.4. Thank you.